Yeah, so hello everyone, and welcome to the Geothermal Rising Tech Talks at the University of Oklahoma. Today's talk is part of the Geothermal Technology class offered by Dr. Salehi. The webinar series will be hosted regularly to address the main challenges and advancements in the geothermal sector. Before I introduce my guest speaker today, I would like to thank the old office who initiated and served the Geothermal Rising Student Chapter in the last term, Dr. Salehi, Caesar, Tubi, and myself. Also, I would like to congratulate the new officers, Caesar Vivas as president, Alex Sidola as vice president, Daniel Tete as a secretary, and Camila as a treasurer. Thank you all for volunteering and good luck with your plans for the Geothermal Rising Student Chapter. Now, please join me to welcome our guest speaker for today, Stephen Pye. Steve has served the geothermal industry for almost 50 years, 50. He started working as a drilling engineer for almost 15 years on both oil and gas and geothermal projects. Then as a drilling manager for 16 years. In the last 17 years, he served as a consulting drilling engineer. Steve worked in many geothermal projects in the US and other countries such as New Zealand, Philippines, Indonesia, Kenya, Chile, Iceland, and Italy. He worked in large projects such as the Geysers and the Salton Sea. He also worked on drilling engineering projects outside of geothermal energy, and the most famous one is the Macondo incident that happened in the Gulf of Mexico. So today, Steve will share with us the development history of the Salton Sea geothermal field. Steve, now the floor is yours. You can start the talk.
Thank you, Majid. Today I'm going to discuss the history, the technical problems, the solutions that we came up with, and the future potential of the Salton Sea geothermal resource. It's hung up, Majid. There it goes. Okay. Can you see the pointer on the screen?
Yes.
Okay. So this is the Salton Sea itself, and then to the south is El Centro and Mexicali, and then on down to the Gulf of California. And so this is a spreading center that was is a continuation of the Gulf of California, and it's bordered by two faults: the San Andreas Fault Zone on the eastern side and the San Jacinto Fault Zone on the western side. And this area has continually seen the Colorado River change course and come in here and fill this lake, actually up to about this point, historically. Then it'd change course and go someplace else. The lake would evaporate and then it'd come back in here and then fill this thing all up with river water and sediments. Then it'd shift and then dry out. So the geologic setting in this area is a tensional fracture system, and the host rock is interlayered lacustrine deposits with evaporite beds. The current Salton Sea, the one that's in this picture, actually developed in 1906 due to a faulty irrigation canal. And it took them about a year to plug that off. And then they put the Colorado River back in its prior banks. And the sea, because of the irrigation that was going on, this is all agricultural land in here. And so the runoff from the agricultural land plus the Mexicali sewer actually dumps into a river that comes into here too. Kind of kept this lake going, filling, and the sea level rise was occurring. In more recent times, in the last few years, the need for fresh water has resulted in curtailing the irrigation or managing it in a way that the inflow into the sea is less than the evaporation. So the sea is currently shrinking. The first known work on the Salton Sea was a CO2 field up in this area, and in the 1930s, and it was used for dry ice, and the wells were quite shallow, a couple hundred feet to 700 feet. Pure Oil Company came in and drilled some wells down in this area, and found the high temperature geothermal system, and found this extremely saline brine that had a lot of potash in it. So they were developing it as a source of potash. But there was a mine that came online in Canada, and it dropped the potash price. So it made this kind of untenable and economically. So Pure got merged into Unocal, and so the people that were working on this are now part of Unocal. And Unocal decided they wanted to develop the geysers, and so they traded some of the land down here to Magma in exchange for some of their money in exchange for some of their properties at the geysers. So that started the electric production at the geysers, and then after a while, looking for other projects to develop, they came back to the Salton Sea. We'll get to the lead and lithium later. Excuse me. So initially, 2 power plants were built, one on the Brawley field. Let me see if I can go back. Brawley field was in this area up here. The Salton Sea Field was down on the border of the Salton Sea in this area. So two 10 megawatt plants were built. One was on the Brawley field, one was on the Salton Sea Field. And they were, their contracts were conventional. The plants, which were operated by Unocal, sold steam to San Diego Gas and Electric in the case of Brawley, and Southern California Edison in the case of the Salton Sea. And those 2 utilities operated the respective generation fields, turning the steam into electricity. And they were our partners in developing these geothermal resources. At the end of the test period, it was decided to develop the Salton Sea and abandon the Brawley field due to its scaling and corrosion problems being worse than the Salton Sea. The focus of this presentation is on the Salton Sea, but I'll talk about Brawley a little bit from time to time too. So corrosion, the 2 problems were corrosion and scaling. So initially we used carbon steel casing as a sacrificial tubing string, and we used 7-inch to 13 3/8-inch casing hung from the surface as tubing, and it had to be replaced every 1.5 years on production wells and every 2.5 years on injection. The corrosion on the carbon steel casing was wall fitting. which makes retrieval difficult because it gets so thin that when you put the slips in the table, it crushes the casing. And we had one incident where the well kicked and it watered up all that casing underneath the BOPs. So that wasn't a very good, that wasn't working very well. Our corrosion outfit, corrosion research lab, suggested we test 9-chrome-1 moly as kind of the next step up that might resolve the problem. And so we retrofitted the entire Brawley field with 9-chrome-1 moly, and it failed in 1.5 years. If you want to put a lipstick on the pig, the pitting corrosion was substituted for the general corrosion, and so we didn't have any trouble retrieving the casing anymore. But it wasn't lasting any longer, and it cost a lot. The result was a corrosion task force was formed to evaluate options and determine where we should go. I ended up as the drilling manager, as the manager of that corrosion task force. And so I know more about the corrosion part than I know about the scaling part, but we'll cover both. So the task force had kind of a disagreement with management, and management came to accept our goals for this task force. So there were people in management that thought that we should just figure out what we could afford and run that in the well, and if it didn't work, we quit. And what the task force decided is we needed to figure out what would work and then figure out if we could afford it. So it's a little different sequence. So we started testing alloys. We ran alloy coupons downhole and pulled them out, and we discarded a bunch of alloys based on either crevice corrosion or cracking or accelerated corrosion. And the next test on that remaining list was to run 2 3/8 inch alloy tubing inside the 9 5/8 inch carbon steel tubing. And in that case, we were able to examine the pitting on the outside in a full-size sample. And that further eliminated what we were actually going to test in the end. And we ran 8 5/8 inch alloy tubing as the final test. That final test, we used a laser profilometer that measured pitting depth and frequency along the inside of the pipe, and then did some extreme value statistics to project the project life expectancy with that alloy. In all cases, the corrosion mechanism was pitting. So 2 alloys had a projected 30-year life of the ones we were testing: Beta C titanium and Astelloy C276, which is a cobalt alloy. We ended up installing Beta C titanium in 2 wells. And the Beta C was quite expensive. And so we were looking at ways of reducing the overall cost. And we did some experimenting with polymer concrete line pipe. That's a styrene carrier and Portland cement has a particle inside it, and then it spun at high speed and lines the interior part of the pipe. And there was a overlay of Inconel 625 on the inside of the connections, and a elastomer that went between the joints. Then it was hung from the surface and went down into a Beta C polished bore receptacle The seals on that polished bar receptacle were chevrons composed of carbon impregnated Inconel 625 wire. So everything was high alloy, and those type of chevrons, of course, have no way to get energized. So you have to energize them with a spring, and so the spring was Beta C Bellevue washers. It was run for 2 years, and then pulled out, and then run back. But it always gave people concerns over, well, is it going to get down behind that polymer concrete liner and chew on the pipe? And so when it was replaced the second time, it was after Unocal had sold off its interest in the project, and it was replaced with titanium grade 29. This is the first time I've mentioned titanium grade 29, but we had tested titanium grade 6.4, and it had cracked. And both the titanium manufacturer and our corrosion people, research people, felt like it would survive fine if we went to grade 29, which adds a dab of palladium or ruthenium to the 6.4, and that turned out to be true. But we didn't initially test it because we didn't have that available. It was under test at the time we sold the project to Cal Energy. So we get to this point of, okay, we've got a couple of wells with Beta C, and the rest are still have carbon steel tubing strings. And if you have to do a well workover every year and a half, and you don't have enough in the budget for that, you sometimes let it go on too long. And then the tubing falls apart, and the carbon steel casing gets exposed to the corrosive brine, the cemented carbon steel casing. And in one case, it perforated that outer carbon steel casing and pressured up a shallow zone. And when somebody drilled a well into that shallow zone, it resulted in a blowout, and the rig cratered into the hole. And so it was decided that we needed to retrofit all the wells with grade 29. And the Beta C, it's been long enough now. The Beta C's lasted 20 to 30 years. The grade 29 has lasted about 30 years. So it's also at about the end of its life now. We ran similar experiments and on the injection wells, and ended up with 2507 duplex stainless steel casing as the preferred alloy. So then it came, well, okay, none of this is cheap. What can we do to reduce the alloy part of the well costs? Well, we were at a significant advantage because the wells produce open holes, so we only had to case with the alloys to the top of the reservoir. The other part was doing a bunch of wellbore modeling and reservoir modeling, because if we could get more megawatts per pound of alloy, it would reduce the cost of the well field. And so the larger diameter production wells will produce more with less alloy if they have enough productivity, KH, permeability thickness. And the problem was the production becomes inhibited by the pressure drop, the friction pressure drop in the two-phase region of the wellbore. So water, briny salt water comes in the bottom that's hot, about 580 to 600 degrees Fahrenheit. It travels partway up the well where the pressure drops, and part of it starts to turn to steam. Then you're flowing at very high velocities with a steam and water mix. And that steam and water mix creates a lot of friction pressure, which then limits the amount of drawdown you can put on the reservoir. So the most productive wells look like 16-inch casing was the best size to minimize the costs, and 13 3/8 casing were the less productive areas. So all the existing 13 3/8 carbon steel wells were retrofitted with 10 3/4 grade 29 titanium. The injection wells are not affected by diameter because it's just kind of linear because there's no two-phase zone or high velocities associated with that. So, like we talked about, what can you afford? And there's been some changes in the contract terms. As I talked about a minute ago, original contracts were steam sales agreements with utilities. That is, we developed the steam field and we sold steam across a fence line to the utility at a certain price per pound. What happened was that we went into a period where the utilities were forced to become transmission facilities and they had to sell off all their generation facilities. For the transition, there was what was called a standard offer 4 contract available for a 10-year fixed period to bridge the transition from the current system to the independent system operator, ISO market, we have today in California. Unfortunately, the pricing under the ISO is marginal to the Salton Sea resource at the current time, which has limited the amount of development that has occurred. So one other thing that we probably need to discuss is what are the differences between some of these things. And thermal stress is an important factor. The thermal stress is the modulus of elasticity times the coefficient of thermal expansion times the change in temperature. And so if you're going to do it in degrees Fahrenheit for the coefficient of thermal expansion, then the temperature change is also in degrees Fahrenheit. So titanium grade 29 has a low modulus, a low coefficient of thermal expansion, and high strength, high starting strength. It's about 130,000 psi compressive strength, tensile strength material. And that results in the stress within the grade 29 staying in the elastic region. By contrast, carbon steel and nickel alloys have a high modulus, high coefficient, and lower strength in about 80,000 at ambient, which results in stresses that exceed the elastic and require that you do a strain-based design. That is, that you allow for strains in the pipe that are in excess of the yield point. There was a new project proposed, and this was 20 years after the wells were retrofitted with titanium, and so the old titanium manufacturing facilities no longer existed, and they were going to have to be rebuilt. And the time to rebuild them and then produce casing for this project was inconsistent with their deadlines. Their deadlines were driven by tax credits. So geothermal could be efficient if it got renewable tax credits. And the tax credits are really set up for solar and wind, who doesn't, solar and wind don't take very long to construct, whereas a geothermal power plant takes a long time to construct. And so they had the same window of time that solar and wind have, and they had to cram everything and get everything done within that time frame to get the tax credits, which then made the project profitable. So with titanium not meeting that criteria, they were looking around for another alloy, and we'd been running a lot of Inconel 625 in the surface piping and the wellheads, and in the joints downhole that were polymer concrete lined, and so that was was used for the next wells. Now the reason we never tested that is Inconel 625 has a very high heat strength, and so it can't be manufactured as a seamless pipe. It can only be manufactured as a rolled and welded pipe. And when you have a rolled and welded pipe, you can only have integral joint connections. We have to change the slide. So limits you to integral joint connections. There were some wedge type threads that had 80% of pipe body yield strength, but the manufacturer and the owner of that technology would not work with us to put it on the Inconel 625. And so the available connections had only 40% of pipe body yield strength. So go back to the thermal stress. Now you've got pipe bodies that are going through yield, and you have a connection between them that only has 40% of the pipe body strength. And so a lot of the compression is going to happen in the connections, and they aren't really suited for it. And so the Inconel 625 was running cemented, but it had some connection failures. We ended up repairing the connection failures with scab liners, but one of the wells, every time we put a scab liner in it, it just moved the stresses around, and that caused another failure. As a result, we needed to figure out how to make these connections last, and we started working with the reluctant manufacturer, and he was willing to work with us this time as long as we were paying the bill. And so we did some testing similar to ISO 12835, where they take the pipe and put it into a fixture and that holds it so that it can't expand or contract, and then heat it up and cool it down, and heat it up and cool it down, and then use strain gauges to monitor how that's moving. Now in ISO 12835, they actually use nitrogen pressure testing and to monitor the leaks, but this particular joint was not a gas tight joint, so we couldn't do that. So we relied on the strain gauges. We tested 2 wall thicknesses, and we tested them for 16 cycles. There was some permanent strains in the thinner wall thickness in the last 2 cycles, and none in the thicker wall strength, but both were considered acceptable. So one well has now been completed with 13 3/8 over the original 16-inch 625 casing. And so far, so good. So we're going to switch into the other cost item for the Salton Sea is solids precipitation and scale. The brine is near saturation with silica at the bottom hole temperatures, and so you end up with a lot of silica scales. Silica takes a while to precipitate, so it doesn't necessarily give you a lot of problems in the production wells, but in the surface facilities and in the injection wells, it piles up a lot of scale. So we checked 2 methods. We did experiments with 2 methods. By experiments, I mean the whole system was changed from one to the other. And that was back in the days when we had those pilot plants. So 2 methods were tested: pH modification and crystallizer clarifier. So if you take the brine and you lower the pH, it delays the precipitation of the silicates. You have to be careful about the balance, because if you over treat with acid, it'll accelerate the corrosion. And if you don't put enough in there, then you've got silicate precipitation. But if you get it just right, it would inhibit the silica until after it got back out in the formation and reheated, and so it would never precipitate. This required keeping the surface brine hot through the system with an injection temperature at the surface of 250 degrees Fahrenheit. Because of system upsets, this process was abandoned after a couple of years of testing. The problem being that we couldn't really balance it with the measuring capabilities. You ended up with some two-phase flow or some carryover of steam, and the measurement system wasn't able to handle all that and manage that, particularly when changes were quick, manage that acid addition. And so we ended up with either corrosion or scaling. It's still used in the binary plants. So the brine goes through binary plants in some, not in the Salton Sea, but in some other areas. And the pH is then brought down a little bit to keep the silicate in solution, and that works okay. You don't have the two-phase problem or that. So in the crystallizer clarifier testing, unlike the pH mod option, where precipitation was inhibited, crystallizer clarifiers intent is to precipitate all the silicates, keep them as non-toxic solids, and dispose of them in a landfill. And so you've got a large chemical plant where you're recycling seed crystals, and then there's a clarifier and thickener to concentrate the solids in a belt press to produce filter cake for disposal. So we found that there was a problem with the sulfate. And the sulfate resulted in precipitation of barium sulfate and strontium sulfate. Strontium sulfate is highly radioactive. And so we ended up having to put inhibition chemicals into the flowing stream to prevent the naturally occurring radioactive materials from forming. And it also turned out that we were very close to the saturation limit for chloride as you remove the water from the system through forming steam, and it required a little bit of water dilution to make sure that it didn't precipitate. The process was successful, and it's the current process in use in all the power plants at the Salton Sea. So I get to some of the other things that were tried and are still being tried. A plant was built to extract lead, but it had a bunch of process difficulties and corrosion of the lead comes out one end, and this horribly acidic clutch comes out the other end and has to get injected into the reservoir. And so they couldn't resolve how to do that in a way that was going to be economic. So they abandoned that project in 2008. There are currently a number of slipstream laboratory-size lithium plants being tested, or some have been tested and put away for use. And various companies plan to move to the pilot plant stage to recover lithium for batteries. The current opportunities in the in the field. California has recently required the utilities to purchase an additional 1,000 megawatts of geothermal power. And they are out to bid to buy that amount of power, which may result in a competitive price that will make further development of the Salton Sea possible. The lithium process may provide some additional revenue if they are successful. Now, the other thing I forgot to mention is with the Salton Sea level going down, quite a bit of, about half the Salton Sea Field is underwater or was underwater. And that, as that continues to regress, the sea level continues to regress, there'll be more areas that can be developed in the Salton Sea Field because they'll be dry. Unfortunately, along with that, they're exposing that toxic materials mix, fertilizer and sewage, and it is a problem somebody's going to have to deal with, because it blows up dust, and the dust is toxic. But other than that, there's good opportunity right now if we can get adequate power purchase agreements under this new additional 1,000 watts of geothermal power. And I think I will stop there and let you ask questions.
Thank you, Steve, for the presentation. I think now the floor is open for questions.
Steve, thanks for the presentation. I have a question. You mentioned about the type of agreements for buying the power. If you can have more information on that, what type of power agreements exist for geothermal projects, or why specifically they chose that fund, I would appreciate that.
So do we need the slides up anymore? I can stop sharing and.
Yeah, you can stop sharing.
So the initial contracts provided a fairly high price for the steam, and the power plant was all dealt with by the utility. When we got to the standard offer 4s, we were getting, a good amount of price for what we were selling. When they went to the ISO bid based on the capacity, the nameplate capacity, and the people with the lowest nameplate capacity bid ended up getting a contract where they sold based on bidding into the ISO. And so prior to that time, there was a capacity payment and an energy payment. After that time, after the standard offer 4s, there was only an energy payment. And the capacity that they were deciding what they were going to buy, so take a solar power, for instance, and you build a 10 megawatt solar power plant, but because the sun doesn't shine all the time, you only get about 4 megawatts out of it. And so when you look at the cost of 4 megawatts and 10 megawatts that geothermal is delivering, it's a lot cheaper in apparent capacity cost, but not in delivery cost. And the other issue was gas got really cheap, and nobody was competing with gas. And so any power they bought, any power the utilities bought from renewable resources was to meet the requirements of the state, because they had to pay more for that than they would have had to pay for gas. And so until recently, geothermal didn't get any special treatment relative to solar and wind, and this kind of designated a certain amount of power to go with that. The advantage that geothermal has that wasn't getting paid for was it runs 24 hours a day. Doesn't matter whether the sun's shining or the wind's blowing, it's running. And so that was the big change. And as we go through more of this, there's going to be more opportunities for geothermal as we decarbonize the fuel source for power as well as other things. But it's going to result in higher costs for electricity. And so there's that yin and yang. Do you want to have clean energy, or do you want and pay more, or do you want to have dirty energy and pay less? And it'll be an interesting to see how that all works out.
Thank you.
Do we have another question?
Okay, I have a question. It's related to the, you mentioned that in the past there were used sacrifice tubulars that they have to replace 1.5 or 2.5 years each time. Now with the new developments and the new alloys, what is the max time that you think that those tubulars will last, considering the long term? The long term that is required for for those geothermal wells.
So the Beta C ended, and it lasted for between 25 and 35 years. The grade 29 titanium has been in service for 30 years. There's been a couple of wells abandoned already or refitted because the grade 29 failed. The failure of the grade 29, there was a couple early on that were just dumb. Titanium is a very soft material, and if you run tungsten carbide hard banded tool joints in there and rub them on it, it makes a hole in it really quick. And so we had a couple of problems that were related to not properly protecting the titanium when they did workovers. So the workovers are still required. You've got problems that happen downhole in the formation. We end up under reaming or redrilling to get rid of the scale that's forming in the formation near the wellbore. I may have gone off track. Did I answer your question? But that's we expect the average life of the 29 to be 30 years, and some of them will probably go to 40 years.
Thank you.
I have a question myself. So you mentioned something about controlling the pH above the corrosion limit and below the scaling. So that specific value, do you do some tests for that, or you just do it by experience?
No, they do tests, and they're still looking at that, walking the line between getting it too low and causing corrosion in carbon steel. This is in the binary plants now, and getting it too high and letting the scale form. But it's used in the binary plants quite a bit because they're taking the last heat out, and that causes more silica to precipitate, even if there was no silica in the fluid going into the binary. Just to put you in, 16-inch grade 29 is about $2,000 a foot, and 16-inch 625 is about $1,800 a foot. These are not cheap materials. The 2507 is not bad. about $400 a foot.
Okay, this is Jamal. Can you hear me? I have a question to ask you. The 25 plus or 30 years you mentioned about titanium, does it also require to have any kind of chemical treatment? Or is without any treatment, it could last 30 years plus?
Yeah, there's no chemical treatments on any of these. That's why we got rid of Brawley. Brawley would have required downhole acidification, and that really complicates things. And but no, there's no chemical treatment. And the thing you have to be careful of is the wear when you're doing workovers, cleaning out scale. There's still some scale downhole, and you have to clean it out.
Thank you.
Okay. We have a question here in the classroom, so okay, Laura.
Hi there. I have a question regarding how the lithium or the lead extraction is performed. If you could elaborate more on that.
Okay, I only am familiar with, and barely, with one of the process because they're all considered trade secrets. And so the one that I'm familiar with, they have to remove everything, all the iron, all the other metals, everything out of that. So it's just pure brine with no metals left in it. Iron being a big problem. And then it goes through a ion exchange resin. And the ion exchange resin extracts the lithium. But it's all the prep work to get it so that there's no poisons for the ion exchange resin left in the system.
Thank you.
I just wanted to add a point for the lithium extraction. I think the DOE right now is hosting a competition between the companies and institutions for lithium extractions. I think the prize is like 4 million. So if anyone is interested, can join the competition.
Yeah, there's a lot of, DOE is also working a lot on trying to make enhanced geothermal systems price competitive too, and that hasn't happened yet, but they're still working on it. So they're supporting a lot of, drill 2 wells, 50,000, connect them with hydraulic fracturing, and then extract the heat from the created reservoir. But that, that's still in the science stage.
Okay. We have another question in the classroom, so Camila.
Hello, thank you for your presentation. My question is, how many production and injection wells do you have? And what was the parameters that you considered to decide that amount?
Well, that's a really good question that I don't have a really good answer for. I can tell you what I know, and then you can. It's one of those things that has evolved. So remember in the beginning we had carbon steel tubing strings that had to be changed out every year and a half, and so we had a lot of extra wells because a lot of them were taken out of service in order to retrieve that casing and replace it. So the most recent project has 3 production wells and 3 injection wells. And so one of the injection wells is shallow and takes the condensate from the power plant, which isn't compatible with the hot brine, and injects it in a separate area. And then you've got 2 brine injectors, of which we normally only have to use 1. And we've got the 3 producers, we normally can get by with 2. Now they scale up, so they do scale up, and so then you have to clean them out, and so that's what the third well is for, so to manage that. Now it's a 50 megawatt plant, so we're getting two of the wells can produce more than 50 megawatts. The third well didn't have the production capacity; it's farther off the flank of that part of the field, and probably only produces 20 megawatts, where the other two can produce 30 to 40 sustained. When we first developed the larger diameter wells, we ended up with a well that could produce 40 megawatts. And then the problem was, what do you do when you shut that well down? Because now you've lost 40 megawatts of your generation. And so in the end, they ended up starting to manifold things together. So it gets more complicated because you got wells in one place supplying steam to different plants. But it's roughly that kind of ratio, 3 producers and 2 injectors, plus a condensated disposal system.
Yeah, okay. We have another question. Here with us.
Hi, how are you? Thank you for your presentation. Very interesting. I just have a question just to make sure that I understood. Larger diameter production wells are gonna always produce more. So in geothermal, it is better to have a larger diameter always, like in all cases, or there are some exceptions.
So if you increase the diameter, you don't get a commensurate increase, which increases the cost, and you don't get a commensurate increase in production, then it's not economic to increase that diameter. So wells that are capable of producing 20 megawatts, if you made the casing bigger, they might produce 25. That's not going to be economic. So the wells that would produce 20 megawatts with the 13 3/8 inch casing, and you put 16 inch down to 2,000 feet, they'll produce 30 or 40 megawatts, then that's economic. So it's those high capacity wells. Those are mostly in what is geologically a breccia chimney and very high variability.
I think that we don't have questions here in the classroom.
If we don't have any more questions, I think we can. Do you have anything, Cesar, to say?
No. I just want to thank our guest, Steve, for the presentation. Very clear, very nice. You talk about very interesting things that are going to be, very important for our knowledge and the projects that we plan to develop. So thank you so much. I don't know.
Thank you for having me.
Yeah.
Thank you, Steve.
I just would like to remind everybody that this kind of talks is going to be regular. Next week we will have another one with J-Egg, and just connect to our social media accounts and as well as the emails to be kept posted about our announcements. And thank you, Steve, for the informative presentation.
Thanks, Majid. Thanks for having me.
Okay.
All right.